Three-phase Y connected 15 megawatt 0.866 lagging power factor load is supplied at 115 kV line to line. The transmission line has the distributed parameters of R prime equals 0.00893 ohms per kilometer, L prime equals 1.554 millihenries per kilometer, G prime is 0 Siemens per kilometer, and C prime is 7.387 times 10 to the minus 9th farads per kilometer. Calculate the voltage at the sending end of the line for a 50 kilometer line. So for a line length less than 80 kilometers, we need to use the short line model. And the short line model is a series inductor and resistor pair. So this would be L prime times L, and this would be R prime times L. So there's only one current flow in this line. It's through those two. This is the voltage on a line to neutral basis at the load, which we on a transmission line we call the receiving end, and this is the voltage at the source, which on a transmission line we call the sending end of it. The line model gives us the characteristic solution equation, which is that the sending end voltage is equal to the receiving end voltage plus I times R plus J omega L, where R and L are the lumped series resistance and reactance of the transmission line. You can calculate it as R prime plus J omega L prime times L, right? So we need to know what the receiving end voltage is. It's on this model is a line to neutral model, so we need to go from line to line to line to neutral. So V line to neutral is voltage line to line divided by the square root of 3. Let's see, this was 115 kV line, so we need to divide 115 by square root of 3. We get 66.4 kV. We will make that our reference. It's the known value. This is line to neutral. We then need to know what the current flow through the transmission line is. We can just get that from the power information related to the load. So the current in the line is going to be equal to the load apparent power divided by the voltage delivered to the load. Take the complex conjugate of that. And so for us, we were given real power, so that's 15 megawatts. That's three-phase, so go to single phase, we'll get 5 megawatts. To go to voltamps, we need to divide by the power factor. And then we need to divide by 66.4 kV angle 0 degrees. And we need to take the complex conjugate of that. And so that's going to give us a, well, I left out a major step there. Hopefully you caught that. I need the angle of the apparent power in the numerator. That is the arc cosine of the power factor. Now we take the complex conjugate of that. So you may have noticed I drew a little minus sign here in front of the cosine. That's how you take the complex conjugate. So just sorry for that clarification there. Anyway, what you should have got was that the load power on a single phase basis is 5.77 angle 30 degrees megawatts. So current is 5.77 angle 30 divided by 66.4 kilo at angle 0. That gives us a current flow in the line of 86.96 at an angle of negative 30 degrees amps for our receiving end, sending end, and line currents. They're all the same in this model. There's only one branch in the transmission line. So I can now calculate my sending end or input end voltage. That's going to be that 66.4 kV angle 0 degrees. I then add to it the product of the current and the series impedance. Current I just calculated at 86.96, angle negative 30 degrees amps, and the line impedance is going to be taken from the problem statement, 0.00893 ohms per kilometer plus J. What do we get up there? Okay, we are given L prime, so it's going to be 2 pi times 60 times 1.554. It was a millihenry, so e to the minus 3, so that's J 2 pi FL. Whoops, that's going to end up being in ohms per kilometer as well, and so now we need to multiply by the line length, which in this case was a 50 kilometer line, I believe. Yep, 50 kilometers. So the sending end voltage of this line on a line to neutral basis was 67.74, angle 1.85 degrees kV, which we could alternatively state as 117.33 kilovolts line to line.